So here we're going to continue talking about our Euclidean M space. All right, so in the previous video we defined column vectors and we took a look at what made a column vector and just kind of the idea about representing excuse me, representing a system as a column vector. We just define a column vector and how we reference the different excuse me, the different entries in the column vector. And now we're going to take a look here as this idea of Euclidean M space is it's a structure that we call a what's called a vector space. Right now, before we get into that, a lot of our intuition behind this Euclidean M space comes from the axioms of real numbers and their properties. Right. So if you see here, so these are axioms for the real numbers. Right. In particular, the first 9 there are what is going to what we're going to lean on a lot. Right. Now, when I say an axiom, it means that this is a foundational statement. There is no proof for these statements. We assume that they are true without proof, and there has been no again, there's no, they always work essentially, right? There's no counterexample that will disprove this. Okay, so these are the axioms over the real numbers, right? The real numbers are a field, right? And our scalars, have we seen, come from the real numbers, and the entries in our Euclidean M space come from the real numbers, right? And that's kind of where our proofs for some of these vector space properties, which I'll get into in a minute, will come from, by leaning on these axioms for real numbers. Okay, and I'm sure we're all familiar with them. If we don't know exactly the name, we know that the real numbers behave in this manner. So before we get into any of that, we do need to define 2 operations in a vector space. Right now, when we move away from column vectors and just general vector spaces, these are the same, well, we'll call them the same operations. How they're defined would be different depending on what the vectors take form, right? But for now, again, we're dealing with the Euclidean M space. So we want to define 2 operations. The first one is column vector addition. Okay, so for column vector addition, right, let's see, we have U and V, element of R to the M. And then the operation U plus V is defined. All right, now again, maybe you've seen that before and you have an idea of what that means, right? But remember, we're defining it. We're establishing this relationship here. Right? Remember, these are vectors, not real numbers. So we need to define what it is to add 2 vectors here. Right? So here is the notation here. For I between 1 and n. Right, so again, it is defined piecewise. Right, we have a piecewise definition of this. Excuse me, not piecewise, element-wise, right? So here, something like the vector 1, 2, 3, 4. Right, then we add across elements, so it's 3 plus 1 over 2 plus 4. Reduces to 4, 6. Okay. All right. So again, right, straightforward. We just want to establish. We want to start. We want to build this structure from these 2 operations, right? and this is the foundation of all of the vector spaces, is we need to have a properly defined operation of how do we add vectors and also how do we multiply them by a scalar, right? So here now we'll define column vector scalar multiplication. All right, or CVSM. Okay, so again, we'll start with some vector u, element of our Euclidean M space, right? And some scalar alpha, which is a real number. All right, then we define alpha times the vector u for, again, I between 1 and m, right? So we define it component-wise, all right? So what that means is, so if we have something like this, and this is 2 times 1, 2 times 2, 2 times 3. Okay, so we define a vector in this form. So that is scalar. Now this is just an example. Again, this is for M space, so it doesn't matter how many elements or in what M space I'm in, right? 3, 4, 5, etc. Okay, right. Straightforward. Again, we're just defining these operations because now once we define them, then we can build on this idea of a vector space. All right, so here, a vector space, so let me switch over here to our textbook. Okay, and we're going to look at the properties of a vector space. So let me switch over here. Okay, so this is subsection VSP, vector space properties. And we're going to look in particular at theorem VSPCV, the vector space properties of column vectors. All right, so it says suppose that Cm is a set of column vectors of size m with addition and scalar multiplication as defined, what we just finished defining. All right, with that definition, then the vector space of C to the m holds all these properties. Now notice here that a lot of these properties are the same ones for the real numbers. They're just an extension to these column vectors. Right? As we'll see later when we talk about just general vector spaces, these properties need to be properly defined for, or these properties need to follow for any other type of vector space that is not Euclidean M space. All right, these same properties will be the same. The way we define the addition and the scalar multiplication would be different, right? So the proof of them would be different as well, right? Now these here are not axioms, right? We've properly defined scalar multiplication and addition of two vectors. So now we can prove these based off of those definitions and also the properties of the real numbers as well, right? So for instance, let's take a look here. I'm going to prove CC, the commutativity of column vectors. Let me switch over here. Okay, so here, so I want to prove property C. Right, so what that states is that if V element of R to the M, then U plus V, the vectors U plus V, is equal to V plus U, right? Again, right, this is a property of real numbers. Well, here, these are not real numbers, right? These are column vectors. So I can prove this using, right, the definitions of a column vector, as well as how I've established what vector addition is, okay? So we'll start with here the definition of, first of all, vector addition, right? We'll start here, right? So for I greater than or equal to 1, but less than or equal to m, then by definition, we have this. All right, and this is the definition of vector addition. All right. Okay, and now if we notice again, right, these terms here, these individual ones, those are real numbers. So I can lean now on the axioms of real numbers to say, all right, well, each of these terms is a real number, so I know that real numbers possess the property of commutativity. Let's say, commutativity of real numbers. Okay, and now I apply the definition of vector addition as well. Reapply it again, but now in this other form. Right, so definition of vector addition. Right, and that's it, right? That gets us here, right? That establishes the proof. So if this is true for I between 1 and m, right, then that means that here we have shown that U plus V is equivalent to V plus U. Okay, so just look at the structure of the proof here. Just leaning on definitions and properties of real numbers, right? Initially, especially for these vector space, that's all we're going to need here, right? As the theorems get more complex, right, we'll add some more complexity to it. But this is all that we are looking for now, right? These vector space properties here.